Oh, what a mess. Okay, so honestly, I don't know if it's the OneNote program or if it's Zoom itself. Yeah, that's not good. Anyway, there's a convention that, so technically this group here is technically up because we've drawn the protons down, and this group here is technically up as well. But we don't necessarily do that because since we've declared that one is down, the other one's automatically up. So whenever there's ring systems like this, like whatever it would happen to be, as long as like one proton's forward and one proton's down, that's telling us that this is trans, or if they're both in the same direction, that's telling us that it is cis. So often we don't actually draw this part being up or down. Like the actual ring being up, we just draw the proton, and that by definition tells us what's going on. So that, how did everyone do with regard to their endo and exo transition states? Okay, so what we'll do is we will do a couple more then. Let's do something which looks like this. Yeah, let's keep it symmetrical. And over here, we will have I'm gonna heat this up. So the core of this will be as follows. So these electrons are going to come here. Those electrons are going to make a bond there. These electrons are going to go there. So 1, 2, 3, 4, A, B. So 6-membered ring. Between 2 and 3, we're going to have a double bond. Right now, we don't know the stereochemistry at positions 1 and 4. But we do know that A and B will be cis to one another. Because this stereochemistry here is dictated by this stereochemistry here. So I've drawn them both up just for convenience. So the two transition states, the endo and the exo, are going to tell us, are the OMEs on the same side, or are they on the opposite side? So endo, exo. Okay, so take a couple more minutes and try to draw the endo and the exo, and we'll compare notes at the very end. Pause this again. It looks like the last little bit, which yes. Okay, so we've drawn our exaggerated version of our diene. Now we're going to add our dienophile. So here we go. The endotransition state, the cyano group will be underneath, and the methyl group in this case is also underneath. And in the exo, this over a bit. Since it's cis, now we want to add our protons on here. So proton, proton, and proton, proton. And over here, proton, proton. The other two blue protons are underneath in this case over here, right? So they're underneath. Now the groups that are on the same side, we'll just circle everything on the right. 4 protons, that's easy. Over here, the cyano group and the 2 protons in the methyl group. So with our endotransition state, you'll notice that all of the substituents, all the protons are on the same side. So our product will look like this. So let's just put all our big groups. Let's just put them down. Or we could put them all up conversely, but I just chose down. So this would be the endo product. All of the groups are on the same side, and I could have drawn in those 4 protons all pointing up, but they're all on the same side. So this would be the endo. And so the thing which will change between the endo and the exo is that in the exo, now the relative position of the 2 OMEs is going to change. So if we've got the cyano group down and the methyl group down, because they're cis, they're going to be on the same side as those 2 protons. So we would have proton down, which means these 2 OMEs are up. So the only thing that has changed between the 2 exo and the endo is the relative stereochemistry on the carbons that are that were originally on the diene. The substituents here, that was dictated by the stereochemistry of the dienophyl. It was cis, so they're both on the same side. So it's just the relative stereochemistry of those 2 OME groups that changes between the 2 transition states. So that's really neat. So right, if you drew all of your OME, your nitrile, your methyl, if you put those all forward, what you've just drawn is the enantiomer, which is totally correct. So right, each one of these products is going to have an enantiomer associated with it. So if you drew the enantiomer, that's perfectly fine. That's good. The key point is that all of these groups in the endo transition state are on the same side. And on the exo, the 2 OMEs are on the same side, but they're opposite to the other 2. That's the key point here. Right. So that's basically the Diels-Alder reaction. There is, I guess if you looked at the second midterm that was posted on Moodle, there would have been a couple of questions based upon this on it, draw the transition state, draw the products. So that's something that you want to be able to do. It's a relatively important reaction. In fact, it's one of the most favorite reactions of synthetic organic chemists, mainly because what we're showing here is that you can generate 4 chiral centers, and depending upon the transition state, you can set it up so that you could make all 4 of these things on the same side of the molecule. So it's quite a powerful little reaction. Diels-Alder reactions are typically, you just heat them up. There's other techniques that chemists have used, putting them in a solvent and then putting them in what we would call a sealed tube and heating them up. So that's got heat, and the added part of would be pressure. Lewis acids can catalyze these types of reactions, mainly because the Lewis acid is will complex to the various groups that are help activate the Diels-Alder reaction. So all these carbonyl type compounds, Lewis acids will help activate them. So it's quite a neat little reaction. So you can do Diels-Alder reactions at high temperature, and you can get away with doing them at lower temperature when they're catalyzed by Lewis acids and that type of stuff. So that is there's all sorts of fun things to do with, like, as I in our upper year course, we do a whole sort of little mini module just on Diels-Alder reactions because they're so neat. When I was working on when I was in grad school, one of the reactions that I did was this. And so this is a double bond here. There was a couple of this R groups here. We tried it with a couple of different things. But anyway, we did this Diels-Alder reaction, which involved these types of, so this diene here is slightly different in the sense it's got a aldehyde associated with it, but you can still do Diels-Alder reactions on these. And so the first step was this. And so these electrons went there, those moved there, those moved there, which gave us this product. OR. Then you'll notice that the neat part is that this is ready to do a reaction with this. And we did a second Diels-Alder reaction. It was all in one pot, so to speak. And do I have an extra? No, that's right. And so this actually may end up making this. And we had a ketone here, or ester here, double bond there, this here, this here. And the neat part is that this stereocenter, this stereocenter, this stereocenter, this stereocenter, this stereocenter, and this stereocenter were all controlled by the type of, was it an Ex0 or Endo transition state and that sort of stuff. So it was, and then how this first reacted was dependent upon the fact that we had these groups here. So it was really kind of neat that you could control all of those stereocenters to make a relatively complex molecule with a simpler sort of starting material. And we also actually had some other parts, interesting stuff here as well, but that's outside. So there's the Diels-Alder reaction is sort of near and dear to my heart, so to speak. Anyway, but the key point for what we want to do is that if we have a diene and we have a dienophile, to be able to draw the products, the Endo product and the Ex0 product. And so you can basically, the fun part about this is that you can practice this by just choosing with your dyeing, so your dynophile, just make sure one of the groups has got like a ketone, an ester, a nitrile, something like that, some sort of electron withdrawing group via resonance. And for your dyeing, just add some substituents on carbons 1 and carbon 4. So I could do a bridge with an oxygen, and our two products would look like, for the endo, this would mean that in this case here, the bridge, the oxygen would be on the same side as the methyl group and that H. So our endo product would be, remember with the Diels-Alder cycloaddition, you always make a 6-membered ring. And if you keep the perspective the same, it'll always be a double bond on the left-hand side. Okay, so we've got, let's make this methyl group up. So that means the cyano group is down. And the oxygen is going to be on the same side. So this would be up. 1, 2, 3, 4. 1, 2, 3, 4. So there's that bridging oxygen between carbons 1 and 4. So this would be the endo. And I know that the Ex0 now is going to be as follows. If I keep everything the same, this would be up. Because the stereochemistry between carbons 1 and 4 is going to be opposite for endo and Ex0 if you keep the other two substituents the same. I can redraw it here to prove that I'm right. And so let's do that. Extend this out. And if we draw in our dynophile, Ex0, the cyano group is going to be way over here. The methyl group will be under. So the group's on the same side. The oxygen, cyano. So the oxygen and the cyano are on the same side. Right, so yeah, so it's one of those games you can play if you got a friend. You can draw some dynes and draw some dynophiles and hook them up, and they will draw the two transition states. And you'll, once you get the hang of it, you'll notice that it's the stereochemistry at carbons 1 and 4 that changes between the two transition states if you keep everything else constant. So, and the key point is that it's the geometry of the double bond which dictates this stereochemistry here, if it's cis or trans. So keep that in mind because this is a stereospecific reaction. Were there any questions on that at all? I'll open up some questions on Moodle for this right after class. The next part of what we're going to do, I guess, what day is it today? Today's Tuesday? Yeah, today's Tuesday. On Thursday, what we'll look at is aromaticity. So we are going to look at, the next functional group we're going to look at is the aromatic rings, like benzene, for example. But we're going to give some basic background on why these systems are so stable. So like a double bond will react with Br2. We did this earlier. But if you put an aromatic ring and react it with Br2, you get no reaction. Unless you do something to make the bromine more reactive. And so we'll basically discuss The aromaticity basically is providing additional stability to these double bonds, which renders them less reactive. But we will cover aromatic rings and how you do chemistry with them. So that's what we're gonna, so next class we'll just do some basic, what are the rules of aromaticity, and then after that we'll do a series of substitution reactions with aromatic rings and the rules of how that works. Alrighty, so I'll try to figure out where all of these recordings are, and so for this lecture it seems like it might be chopped up into little bits. Okay. I will see everybody soon, and hopefully I'll figure out what's going on with this computer of mine. But anyway, have a good day. Okay, so I will end this.